So let us define MPNNs, message passing GNNs. So I'll start with an uh, figurative illustration. So here we have the embedding at step K. HUK is the embedding of U, and HVIK is the embedding of VI. Okay, now at the kth step, we basically construct a message from the embedding of U and the embedding of V, and possibly with the features of the edges, E1, E2, E3. These three components comprise a message. Okay, so now we have three messages because U has three neighbors. Okay, in order to update the value, the representation of U to be the K plus first version, we aggregate these three messages. Okay, and we'll see how we do that. But basically, this is the idea. Okay, so if UV is an edge, we define a message function to be a function that takes as input two embeddings, U and V, two representations, and produces a new vector of dimension dm. Okay, that's very simple. Okay, and if we have an edge feature, xe, then it is also accounted for. So m is a function of xu, xv, and x of the edge between u and v. Okay, therefore these are the dimensions, the 2d plus de to dm. All right, now usually, as we did previously, we assume that there are no edge features. Okay, unless I state so explicitly. Okay, the default is that there are no edge features. Okay, so a message passing layer is a function that transforms the feature vector xu, okay, of the node of u, into a new vector um, that comprises the messages that incorporates basically the messages of the neighbors. Okay, so this is how it looks like. Lambda, capital lambda of G and U is basically a function that consists of three inner functions. One is the message M between XU and XV. Okay, applying this message to all of the neighbors of U, V belongs to the neighborhood of the neighbors of U. We get a collection of vectors. We view them as a bag of vectors because there might be duplicates, but it is unordered, right? It's like a set. Then on this bag, we apply alpha, the aggregation function. And this can be sum, average, element-wise max, uh, or whatever aggregation function, as long as it is a function over the bag. It doesn't assume any order. Okay, so this is alpha. Then we get XU and the aggregated message. Okay, and this is the input of U. U takes these two and produces the output of the message passing layer. Okay, so we have three functions. M is a message function. Alpha, aggregation function, takes as input a bag and produces one vector. Okay, and U takes the combination of XU and the aggregated message of the neighbors and produces a new vector. Okay, in terms of the dimensions, so M is from 2D to DM. Then alpha takes bags in RDM and produces a single vector in RD prime. And then U takes a vector in or input of size of dimension d plus d prime, okay, and produces a new vector of dimension d prime prime. And it is often the case that the d and the d prime are the same, and so you will be from 2d to d prime prime. Okay. In this case, we will say that lambda is d to d prime prime layer. Okay, we show how to use it. Uh, Now, do realize that in principle, each of the three functions can have parameters. Okay, and we omit them from the abstract representation, but it can be parameters. Usually, alpha doesn't have parameters. It's a simple function like average and so on, but it can have parameters. Okay. Uh, Now, do realize that these parameters are not shared, okay, unless we say so explicitly. But by default, when we say, parameters theta of this one, of then theta prime of the other one, these are disjoint, okay? Of course, they are shared among nodes. Okay, we need to learn something. Something needs to be shared. So for all of the nodes, use the same function, use the same update function using the same parameters. But among the three functions that we have that define the message passing layer, there are no shared parameters. Okay. So now, once we have the message passing layer, we can define a message passing GNN, okay, or an MPNN. This is a chain of message passing layers. Uh, each layer is a dk minus 1 to dk for k equals 1 to L. Okay, D0 is D, the original dimension of the source nodes, here the features of the source node. Okay, so then it is defined as follows: HU0 is the original set of features, the sequence of features, XU. Okay, and then HUK is update K of what? The previous representation, HUK minus 1, comma, the kth aggregation, alpha k, applied to the messages that we obtain from, again, the previous layer, HUK minus 1, HVK minus 1, for all neighbors V of U. Okay, so this is the definition. And we may use also lowercase m, muk to denote the aggregated message, okay, which is alpha k applied to the messages of the neighbors, okay, using mk, okay, and using the values of the previous layer. So that would be muk. Okay, therefore, the kth value, the kth representation is uk of hu k minus 1, the previous layer, comma, the message, the aggregated message of u, which is muk. Okay, so this is how it looks like. This is an illustration of two layers, okay, a two-layer MPNN. So how does the information flow? So this is our graph, and we're looking now at this node A. So A has three neighbors, B, C, and D. B gets its messages from its neighbors, A and C. C gets a message from its neighbors, and D gets a message. That's the first MPNN layer, message passing layer. Okay? And each of these updates its representation using the aggregated message. That's layer 1. Then layer 2, each of these messages is again entering the aggregation, which is used for updating the representation of A. Okay, that's the second layer. Okay, now the output layer. So the way we define an MPNN, The result is the output of the last layer. It's basically the last layer HUL. Okay, L is the number of layers. Okay. Now, when you complete GNN to a full task, usually there is some decision layer on top of the last embedding layer, okay, which looks like, say, an MLP, or it can be some feed forward on top of the last layer. And then it is typically complemented with something softmax when you want to do, say, multi-class classification. Okay, that's for no-level tasks. For graph level, for graph level tasks, usually you have some uh, what is called a readout layer, which is basically obtained by a new aggregation over the set of all embeddings. This is capital HL, having a row for every node, okay, the last layer of every node, and then followed by DNN, the contract standard ones like MLP and softmax. Okay. Later we'll also discuss link level tasks, which are different that require some different viewpoint. Okay, some notes on the definition. Uh, we need to be able to learn the GNN, like any machine learning model, any deep learning model. So we assume that all of the functions are differentiable. Okay, and then we can use gradient-based machine learning like Adam optimizer and so on. Okay. I can also use stochastic gradient descent, but the question is, what is the batch there? This is something that we're going to discuss in the last part. Okay, now we assume that there are no parameters that are shared between the layers. And again, unless explicitly stated otherwise, but again, every time we define a new thing, with or a new layer with this k in parentheses in the superscript, the assumption is that it uses fresh new parameters. Okay. Now, I'll just say that when there are edge features, the function, well, basically the MPNN looks the same, except for the function M, the message function, that again uses the features of the edge as part of its input. Now notice that MK uses XUV, the original edge features. The edge features are not updated, okay? We are not maintaining any embedding of the edges. We're just using the same edge features, original edge features, as part of this function M, as part of the message function. Okay, so that's important. Uh, do realize that we are using the graph structure basically to define the MPNN conceptually, but it is a special case of a deep neural network. Okay, and you can view it as basically a function over matrices. Okay, which is the more standard way of looking at deep learning, where the input matrix is X, with the sorry, the input is A and X. Okay, the beginning, the initial embedding is X, and then each HK is some DNN function FK, or DNN unit FK, applied to, well, the adjacency matrix A, then the previous matrix HK minus 1, okay, of the previous layer with the parameters. Okay, so in this way, we can really view the GNN as a deep neural network. Okay, but it is important that this F is equivariant. Okay, it is a permutation equivariant in the sense that we saw previously. If you permute the adjacency matrix and the features, okay, or sorry, the embeddings of the previous layer. Basically, if you rename or reindex the nodes, as we see here with the permutation matrix, then basically you get the same result with the rows permuted in the corresponding way. Okay, so it is important that our f will be defined in this way. And the way we define it is indeed like that because we're using an aggregation function over bags. Okay, a special case is that of simple MPNNs, where basically the message is very simple. It just copies the message, the representation of the neighbors. Okay, here it's xv, but it can be hk minus 1 of v. Okay, it doesn't mean that everything is linear because you still have the update function u, which can include some nonlinearity. Okay, but basically, in the simple case, which is also common, you just copy the embedding of the neighbors. Okay, and aggregate them using the aggregation function. Okay, for example, the aggregated message can be the average of the neighbor messages. Okay, so it looks like that. HU0 is XU. HUK is UK of the previous representation, comma, aggregation K, alpha K, of the neighbor's messages. HVK minus 1 for V in the set of neighbors of U. Okay, so it looks like that alpha takes as input the values, the computer representations of the neighbors. Okay, and um, for example, alpha can be sum, and then this is taken as input of for U. In addition to alpha, U also takes HUK, okay, and produces HK plus 1 of U. And so as a result, after applying this layer, this step or round, we are getting this round where every value is with the superscript K plus 1. Okay, the output of the K plus 1, K plus first layer.